Welcome to the Deep Dive. Today, we're doing something pretty radical. We're moving way beyond standard cosmology. So you can put Einstein and Dirac on standby for a moment.
Yeah, this is a big one.
Because the sources you shared with us introduce a concept so vast, it really challenges the foundation of how we see reality itself.
That's right. We are diving deep into what's known as the theory of infinite hierarchical nesting of matter, or TIHNM for short.
TIHNM.
Okay. And this theory, it doesn't just say that cosmos is, like a fractal, a structure with repeating patterns.
Right, which is an idea that's been floated before.
It demands that physics itself must be self-similar across all scales. I mean, from the tiniest elementary particles right up to entire galaxies.
So our mission today is to really unpack this. This discrete, self-similar cosmological paradigm. It's a mouthful.
It is.
But if we think of, say, the atomic world and the stellar world as being run by totally different rules, quantum mechanics down here, general relativity up there, this theory says no.
It says they're actually morphological copies of each other, just scaled up or down by an absolutely immense factor.
And what's so fascinating is the philosophical promise behind it all.
Exactly. The idea is that the unity of the universe is basically guaranteed because physical phenomena just repeat. They repeat themselves at these fixed, discrete levels.
The atomic, the stellar, the galactic levels.
And this constant repetition reveals what they call the symmetry of similarity.
Okay, that right there implies that the fundamental laws of nature are scale invariant. But, how do you even begin to prove that? Or quantify it?
That's the key question. And that brings us to section 1, the principle of self-similarity. This is where they introduce something called the scale dimension.
The scale dimension.
Precisely. They argue that because nature is so clearly stratified into these levels, if you look at the carriers of matter, an electron, a star, you see the fractality of the systems.
And that leads them to suggest there's another degree of freedom.
Yeah.
Beyond, up, down, left, right, forward, back.
Yes, a scale dimension. So the universe isn't just structured in space, it's structured by scale. And to quantify this, they jump right into a grand analogy.
The hydrogen atom versus a planetary system.
The simplest system they can find. And this is the foundation for all the math that follows. They take the hydrogen system, a proton with an electron orbiting it, and compare it to a typical solar system.
And the parameters have to be, just wildly different.
Oh, completely. For the planetary system, you're looking at a mass of around 1.1 times 10 to the 29 kilograms.
Okay, huge.
With an orbital radius measured in trillions of meters.
And then you contrast that with a hydrogen atom.
Where the proton's mass is, it's almost nothing. 1.67 times 10 to the negative 27 kilograms. And the orbit is measured in picometers.
Right. And the sheer difference in that magnitude is where they get their magic number.
That's it. They take the ratio of the corresponding masses, the huge stellar mass divided by the tiny atomic mass, and they calculate what they call the mass similarity coefficient. They call it phi 0.
And this number is?
It's staggering. It's approximately 6.654 times 10 to the power of 55.
10 to the 55? That's a 6 with 55 zeros after it. That number it's hard to even think about.
And according to the theory, that single number is the constant of cosmic scaling. It should pop up everywhere.
Wow.
And here's where it gets even more intricate. This isn't just one giant leap from an atom to a star.
Oh, really?
No. The research explicitly states there are 9 intermediate levels of matter nested between the atomic level and main sequence stars.
9 levels. What?
Everything from molecular complexes on up through low-massive planets. It's a very strict, step-by-step hierarchical structure.
Okay, I have to pause on that phi 0 coefficient. Because if this theory is right, it means the force laws governing a proton and an electron are mathematically identical to the laws for a star and its planet.
That is the massive claim, yes.
That's a huge claim.
It is, and they use the consistency of that number to justify it. They even extend the analogy to really dense, compact objects.
Like what?
Well, think about a proton, which is incredibly dense, and then compare it to a neutron star, probably the densest thing we know of besides a black hole.
Right. So the source gives the proton's radius as less than a femtometer, and they use the speed of light as the characteristic velocity inside it.
And they compare that to a neutron star, where the internal velocity is a bit slower, but still, highly relativistic.
And by applying these similarity coefficients, they can actually make predictions.
They can. That's the practical side. For example, they can calculate a stellar Planck constant that would describe quantum-like behavior appear at the level of these compact stars.
A Planck constant for stars. And what's the value?
It's calculated to be about 5.5 times 10 to the 41 joule seconds.
Which I guess makes a kind of logical sense if you accept the premise. You're measuring the quantum of action for something 55 orders of magnitude bigger.
Exactly, so the constant has to scale up proportionally. It shows they've built a cohesive mathematical framework, even if the premise is, well, unorthodox.
Very. Okay, so if the mathematical structure repeats, what about the makeup of the universe? That takes us to section 2, where things get really strange.
Yes, they do.
We're talking about the discreteness of matter and something they call a stellar periodic table.
This is maybe the most shocking claim in the whole body of work. The authors found that almost all main sequence stars, the bulk of stars out there, correspond by mass to elements of the periodic table.
Hold on. You're telling me that if you line up stars by their mass, they follow the pattern of, what, hydrogen, helium, lithium, carbon?
That is precisely the claim.
Like a giant cosmic version of the chart from chemistry
Oh,
class.
exactly. And they say the correlation isn't just rough. They assert the inaccuracy is tiny, only 10 to the minus 6%.
That's extraordinary. It suggests the same organizational laws are in play.
And this makes no intuitive sense based on what we think we know about star formation, which is all about gravity and fusion, not atomic numbers.
Right, but the theory claims this correlation goes even further. It's not just mass, it's also about abundance, right?
Yeah.
How common they are.
Yes, the abundance correlation is their key piece of evidence. The number of stars they observe aligns with the abundance of the corresponding atoms.
Give me an example.
Okay, so stars in certain spectral classes, K2, G5, G1, and F2, are observed to be deficient. There are fewer of them than you'd expect.
And what elements do those line up with?
They correspond to elements that are also known to be deficient in the Sun and nearby nebulae: nitrogen, fluorine, sodium, and phosphorus. The pattern of rarity repeats.
That's a very compelling piece of empirical evidence, even if the mechanism is a complete mystery.
It is. And they also mention the famous iron peak.
Right, in nucleosynthesis, where breeding heavier elements suddenly costs energy instead of releasing.
They say that exact same peak repeats in the stellar world. There's a noticeable rise in the number of stars in spectral classes B8, B9, which have masses around 3.2 solar masses.
So the same pattern, the same formative process, seems to control both atomic and stellar creation.
That's the argument. Whether you're in a chemistry lab or mapping the cosmos, you're seeing the same fundamental patterns of scarcity and abundance.
Just scaled up by that phi zero factor. So if stars are the atoms of the next level up, what happens when we zoom out to the galactic scale?
At that point, the theory looks at our Milky Way and sees it as a kind of massive rotating gas cluster, where the stars themselves are just playing the role of atoms.
It's just fractals all the way up.
And this lets them derive specific formulas for galactic structure. For instance, they give a formula for how density changes as you move out from the center of the galaxy.
Let's not get lost in the math, but what does the formula tell us? What's the takeaway?
It basically says that the density drops off steeply as you move away from the galactic center, but it does so in a very predictable, mathematically defined way that fits their whole self-similar model.
Which brings us to section 3. And this is where we have to confront the biggest paradigm shift of all. Because if this scale similarity is real,
Then gravity has to be redefined.
right, conventional general relativity just won't work anymore.
Absolutely. The theory completely ditches the idea of gravity as the curvature of space-time.
Okay, so what is it then?
Instead, gravitation is an effect that arises from the action of incredibly small, relativistic particles that fill all of space. They call them gravitons.
Now, that sounds a lot like Lessage's theory of gravity from, the 18th century. The idea that gravity is a pushing force from tiny particles.
It's very similar.
But didn't that theory fail? I mean, Maxwell and Poincaré showed that all those collisions would heat matter up so fast it would just vaporize instantly.
That was always the classic knock against Lessage's model, yes. But this is a modernist version. They try to solve the energy problem by accounting for where that absorbed energy goes.
So what's their solution?
Well, early ideas suggested it produced magnetism and heat, maybe even providing the energy source for stars. And this model goes a step further. It introduces scale differentiation. Normal gravity, caused by gravitons, applies to stars and planets. But down at the nucleon level, you get what they call strong gravitation.
Okay, so a different kind of gravity for the nucleus.
Correct. And strong gravitation is caused by fluxes of even smaller, more energetic particles they call granons. And here's the radical conclusion.
Go on.
The strong nuclear interaction, the force that holds atomic nuclei together, is not a separate fundamental force at all.
So it's just a consequence of gravity, scaled down.
Precisely. The strong force is gravity, just operating at the nuclear level, driven by these high-energy granons. It's a unification of gravity and the strong force.
Wow, that's a way to unify physics that completely bypasses things like quantum gravity or string theory.
It does.
So how does this vacuum full of particles account for relativistic effects like time dilation?
The movement of rulers and clocks is seen as movement relative to the local vacuum. That vacuum, defined by the constant influx of graviton fluxes, creates the reference frame. Moving through it is what causes the effects.
So relativity isn't about the observer, it's about your motion relative to the local state of the vacuum itself.
That's the idea. It's a way to ground both special and general relativity in the physical properties of a vacuum. And of course, a theory this sweeping has to have its own explanation.
Starting with the big one, the expanding universe. TIHNM rejects expansion, doesn't it? So how does it explain redshift?
It explains redshift not as galaxies flying away from us, but as light itself losing energy, a sort of tired light model. The light quanta simply lose steam as they propagate across vast cosmic distances.
And what's their evidence for that? Because the expansion is pretty well established.
They point to the observed periodicity of redshifts in galaxy clusters. They argue this regular spacing is hard to explain in a standard, dynamically expanding universe.
Okay, and what about the cosmic microwave background, the CMBR, the echo of the Big Bang?
No Big Bang, no echo.
So what is it?
In this model, the CMBR is simply the average temperature of new particles that are constantly being produced everywhere. The universe is always generating new matter, and the average temperature these particles reach is calculated to be a few Kelvin.
Which just happens to match the observed 2.7 Kelvin. So it's an ongoing process, not a fossil from the past.
Exactly.
Okay, that's a total paradigm shift. An entire universe built from the ground up on this one principle of self-similarity. Before we wrap up, let's just, for a moment in section 4, ground ourselves in the scientific methods at play here.
Yeah, we have to look at the context. The prevailing paradigm rests so heavily on giants like Einstein. His work in 1905, then general relativity in 1915.
And in 1917, he introduced the cosmological constant to create a static universe. That was really the birth of modern theoretical cosmology.
It was. And he used theory deduction to build a model, which was later changed based on observation. But when you look at TIHNM, it's based so heavily on observing patterns.
Like the periodic table connection.
Right. And that's a classic epistemological battle, deduction versus induction.
Newton, for instance, was all about induction. You infer causes from what you see. You gather facts, then you find the law.
Which is very much what the TIHNM researchers are doing with their stellar mass correlations.
And the counterpoint is someone like René Descartes, who was searching for absolute certainty through pure deduction, starting with, I think, therefore I am.
Right. And the sources point out that Descartes really struggled when he had to apply that to messy physical systems. He had to fall back on his theories being only morally certain, good enough for practical purposes.
Which really highlights the philosophical divide.
Yeah.
It goes all the way down to how you see causality itself. Hume said we can never prove a necessary connection. It's just an idea in our minds.
Whereas John Stuart Mill argued the opposite. That the necessary connection, the fact that one event unconditionally follows another, is a real thing in the world. And a theory like TIHNM depends entirely on Mill's view of being correct.
It has to be. The repeating patterns can't be random. They have to be governed by a real, necessary law of scale similarity.
So examining this theory forces you to confront those choices. Do you trust the patterns from empirical observation, or do you stick with the paradigms built from the powerful deductive logic of general relativity and quantum field theory?
So the key takeaway here is just realizing that there are these comprehensive, mathematically rigorous, alternative frameworks out there. They offer a completely different view of gravity, of cosmic structure, all driven by scale symmetry.
I think so. And the relevance for you, for anyone listening, is that studying an unorthodox theory like this forces you to identify the core assumptions you take for granted in established science. It makes you ask, where do the rules actually stop and start?
And that brings us back to one of the most powerful ideas in the source material.
The transition point.
Exactly. They suggest that the jump between these discrete matter levels, the moment where quantity becomes a new quality, happens when the number of parts in an object, the exceeds the permissible limit for that one.
It's a boundary condition where the old system breaks down and a new one has to emerge.
That's a fascinating final thought.
It really is. So think about this. In your own life, where have you seen a massive accumulation of quantity? A number of people, a number of data points, a number of small events suddenly flip a switch and create a totally new quality. A new organization that couldn't be understood just by looking at the parts. That boundary, where measure breaks down and a new fractal level emerges, might just be one of the most fundamental processes in the universe.